Of all the computers that I've owned through the years, the one that I have the most love for today is the ZX Spectrum, brought out by Sinclair in 1982. I got mine in 1984 when I was about 11 years old, and I quickly developed a love for computer programming using the built-in language BASIC. I was a bit too young to really get to grips with what's called machine code. Z80 assembly language, the Zilog Z80 processor. It's a very different way to program than the high-level languages that we're used to, such as BASIC and today languages like Python, C++, JavaScript and whatnot. Assembly language is tough as nails. But I've decided to try and get to grips with it now, 35 years later. You might wonder why. It's really because there's a brand new Spectrum computer coming out very soon called the Sinclair Spectrum Next. And I'm very excited about it. It's really a nostalgia product for the over 40s. Well, there's nothing wrong with that, is there? But the thing about it is there has always been, right up until today, a bedroom coding scene revolving around this computer. People still make games for this computer just purely out of their love for the machine and out of their own personal interest. And if anything, the Next is going to keep that going even longer, the Spectrum Next. So I have put my pledge into the Kickstarter campaign. There's still a little bit of time left in that campaign if you're the sort of person who might be interested in this. The link is in the description below. But if I really want to get the most out of this machine when it arrives, I'm going to have to learn assembly language. So I've been doing that recently, and it's all starting to finally make sense to me. So I thought I would provide a tutorial for anybody else who might be struggling to get to grips with this. So you can consider this a first lesson in Z80 assembly. So we're going to do it using emulation on a PC. There's various ways that you can do this, but I have found the easiest way is to use a ZX Spectrum emulator called Spin. And again, I'll put the link down in the description. Spin is a particularly good emulator because it has a built-in assembler. Once you launch the program, you just have to go to Tools and then Z80 Assembler, and it calls up a separate window allowing you to program this virtual Spectrum directly. So that's what we're going to do. Now, the first thing you need to do before you do any assembly language programming is you have to have at least some small knowledge about how the Spectrum's memory is organized. You have to do this because when you program in machine code, you're programming the memory directly. That's not the way it is with high-level languages today, where you just type your script in, you compile it, and you don't have to care where it sits in the memory. Your operating system will take care of that for you. In terms of programming in machine code, you have to know exactly what position in the memory that you're going to put the code into. So here's how the memory is organized on the ZX Spectrum 48K. It's a little different on the 16K, and it's a little different again on the 128K computers, but the 48K was the popular one. It's the one that I owned when I was young. So the memory is addressed from 0 through to 65535. Now that number, if you know anything about kilobytes, you know there are 1024 bytes in a kilobyte. 65535 is exactly 64K, 64 kilobytes. So you might be wondering, I thought this was a 48K machine. Well, the first 16K, which is addressed from 0 to 16383, that 16K is the ROM. The the read-only memory. And it contains, among other things, the basic language that boots up immediately when you switch your Spectrum on. So there's not a lot you can do with that. You can certainly tweak it if you want to, but once you turn your Spectrum off and on again, it reverts back to its original state. It's a ROM chip. It can't be overwritten, only temporarily. But we're not going to concern ourselves with that. We just need to know where it is so that we don't tamper with it. The memory locations from 16384 through to 22527 correspond to the screen itself, the pixels on the screen. And the best way for me to explain this is if you had a Spectrum and you remember loading games in, as the data was loading, there was usually a loading screen that appeared. So that data was loading directly off the tape into the memory registers from 16384 to 22527. And as it did so, the CPU in the computer, the processor, knew that it was supposed to automatically display this on the screen as actual screen data. Okay, so there's a direct relationship between these memory locations and what appears on the screen. You don't have to do like a print instruction or something, it just appears. If you put something in 16384, something will immediately appear at the top left corner of the screen. That's just how it works. But those are just black and white pixels. The color comes after that, and it's stored from 22528 through to 23295. That's where all the color attributes are stored, and they're done in blocks, chunky blocks of 8 pixels across and 8 down each. You'll get a sense of that later. Just bear in mind that it's like 32 blocks of color across and 24 down the screen vertically. There's then a small area of memory from 23296 through to 23754 that is reserved for printer buffer and other bits and pieces, and again, you just don't tamper with that, you leave it alone. Now we come to the main area, the big area from 23755 through to 65367. That is the large area where you will store any programs that you write. Now you'll notice that I didn't go directly to 65535. That's because there's another small area from 65368 to 65535. Again, that is reserved. One of the things that is stored in there are the UDGs, or user-defined graphics, which you might remember if you did a little bit of basic programming back in the day. Again, we're not going to tamper with that. In this lesson, we're just going to be concerned with the screen attribute area. That's the colors from 22528 to 23295, and the main block of usable storage from 23755 to 65367. Okay, are you still with me? I hope so. Right. In our assembler then, the first thing we need to do is type in what's called a directive that tells the assembler where to store the program. And we do that with the directive instruction org, O-R-G, followed by any number that you like, as long as it's within the correct range that we specified. So I'm going to store this program at location 50,000 in the memory. Now you might ask, why don't you just do something logical and start at the very beginning? Put 23755. Well, I'm not going to do that because the Spectrum expects a basic program to be stored at the very beginning of this. If you remember loading games back in the day, they always started with a short loader which was written in BASIC, and then that loader would then load all of the machine code and then it would run it. So no matter what we do, we're always going to start with a very tiny program in BASIC. So it's not advisable to start your machine code at 23755. I'm starting it at 50,000 because why not? What the hell? We're only going to write a short program, so we'll just slap it right in the middle of the Spectrum's memory at location 50,000. So there's our first instruction. Org, which I think is short for origin, the origin point of the code, 50,000. Now what I want to do in this lesson is create a checkerboard effect all over the screen. So in other words, just like a chessboard, black and white squares all over the screen. So let's start small. Let's try and get a black square at the top left corner of the screen. Now here's how I'm going to do this. I know that the first color attribute area at the top left is location 22528. So what I'm going to do is I'm going to store that location in a register called HL. And here's how I do it. I use the command ld HL, comma, 22528. That is very like the instruction in BASIC, which would be let HL equal 22528. Registers are something like variables, and the register I'm using is called HL. Unlike variables, you can't just call them whatever you want. There are very specific registers available for use. HL is one, and H stands for high and L stands for low, high, low. The other register is A, which is the accumulator. There's also B, C, D, and E. BC can be put together just like HL is together, and D and E can also be put together in the same way. You might wonder, why do we do that? Well, register A can store any value between 0 and 255. That makes it an 8-bit register. Bear in mind that the Spectrum is an 8-bit computer, right? But HL can store 16-bit numbers. That means any number from 0 to 65535. So the basic rule of thumb is if you're using a register or a register pair, such as HL, if it's 2 letters long, you can store a 16-bit number in it, but if it's only 1 letter long, you can only store an 8-bit number in it. So we couldn't, for instance, do LDA, comma, 22528. It just wouldn't be accepted. We have to use either HL or DE or BC. So we've stored the value 22528 into the register HL. Now bear in mind that I've said they're a bit like variables. They are and they aren't. HL isn't actually stored in the memory anywhere. It's actually in the processor itself. So we don't really use registers for any kind of permanent storage or long-term storage. They're locations within the processor that we allocate values to because we're going to do something to it very soon. You would store, variables would be stored in actual memory locations that you would choose later, but I don't want to get things too complicated. For now, you can just kind of think of HL as a variable, just to keep things familiar. Now, in order to get that on the screen, we're going to use another instruction. LD, brackets, HL, close brackets, comma, 0. Now, LD with brackets means the actual memory location. When you see the brackets, in this case, it means put the 0 in the actual memory location indicated by HL. It doesn't mean put it in the HL variable. It means put it in the actual memory location indicated by HL. Vastly different meaning, okay? Now you might be wondering, why can't I just do LD brackets 22528 close brackets comma 0? Because that's the sort of shortcut that you would use in a high-level language. You can't do it in assembly language because LD brackets HL is not two separate entities. LD brackets HL is actually a single instruction that takes only 1 byte of memory to store. Just like LDHL without the brackets is a single instruction that takes 1 byte to store. So that's just how it works. It will become clearer to you with a bit of practice. And the last thing we need to do is simply to put RET, which is short for return, and that will return the program back to basic after it has been run. So let's see if this actually works. Now I'm going to go over to the main display of my emulator. I'm sorry, before I do that, I have to actually compile my code. So if I go to File and Assemble means compile, hit OK. No errors in 5 lines, so it looks good. Let's now test it. So back over to the Spin main window. So I'm now going to type something into Spectrum Basic. I'm going to write a short program, 10, randomize, user 50,000, enter. So there's my little program that when I run it, it will execute the machine code stored at memory location 50,000 and beyond. So let's now type run on the R key, enter, bingo. I've now got a black square at the top left corner of the screen, exactly as I expected. Okay, so far so good. The next task then is to get a white square next to it on the right, next to it horizontally. So I'm going to add another line before RET, and what I want to do is point at the next memory location after 22528, which is 22529, and all I've got to do that is to increase the value of HL, and I do that with the instruction INC, INC HL. Now let's put another line in. We want to do LD brackets HL, close brackets, comma, and we want to pick a different color. I'm going to pick color 127. You can pick any value between 0 and 255. I happen to know that 127 is bright white, so that's why I'm choosing that. But you can experiment with values of your own. Okay, let's compile that again and see what happens. And let's go back to basic and press run again. Perfect. I've now got a black dot followed by a white dot. So our next task is to get a whole row of these going. So there are 32 columns across the screen. I'm already using 2 squares out of those 32. So I need to repeat that black and white square 16 times in order to fill the full width of the screen. Now, a really lazy way to do that would just be to repeat the same code that I've written over and over again. That will take considerably more memory than using a simple loop. So we might as well learn how to do a loop. Now, I'm going to add another line in here to match line 4. I need another increment line, increment HL. There we go. So I want to loop lines 3 to 6 16 times. So I'm going to insert a new line above line 3, and I'm going to use another register, this time register B. Load register B with the value 16. Okay, so 16 is now remembered in register B. I'm going to go down to line 8 and insert another line above ret. And what I wanted to do is I wanted to count from 16 down to 0 and loop back to line 4. counting down with each iteration. So in other words, first time running lines 4 to 7, B will be 16. Second time running lines 4 to 7, B will be 15. Third time, B will be 14, and so on. So it's a little bit like what you would know as a for next loop in BASIC, except we're going to do it in the fashion of a countdown rather than a count up. So here's how it works. I'm going to use the instruction D, J, N, Z. Now, after that, I have to tell it where I want to loop back to. So you can think of this as the instruction next, right, in BASIC. But I have to loop back to line 4. But I can't just write line 4 because there are no line numbers the way there are in BASIC. Although there are line numbers appearing in the spin assembler, they aren't actually part of your code. The assembler allows me to put a label in front of any line, which I can use as a point of reference for a particular memory location that I can call later. So I'm going to call this row. I'm going to tab across. I'm going to tab my whole program across so that row is kept on the first tab. Okay, so you can think of that as a label that you can refer to and call. So DJNZ followed by row. Very confusing looking. I forget what the DJ means, but NZ stands for not zero. And here's what that weird looking command actually does. It takes a look at the B register. It takes 1 away from it. So if it's 16, it becomes 15. It checks whether it or not it's 0. If it's not 0, it jumps back to row and it continues processing from there. So again, it'll arrive back down again, then it'll be 14, it'll jump back up. So when it's down to 1 and DJNZ is processed again, the B register becomes 0. And now that it is 0, it doesn't jump back to row, but it continues on down to line 9, and line 9 ends the program. Now, you might say to me, well, why does it do all that? Because there's nothing, in a high-level language, we're used to all those little pieces being specified, all those little bits of logic being specified. They're not specified in these mnemonics in assembly language. You just have to remember what the commands actually do. So contained within DJNZ is the process take away 1 from B, check whether it's 0. If it's 0, end the loop. That's what it does. If it's not 0, if it's not 0, go back to wherever you're going to. In this case, the memory location indicated by the word row. Okay, so when this is compiled, row becomes a particular memory location, and it's translated by the assembler into that. It's very handy that you don't actually have to work out what the exact memory location indicated by row is. It does it all for you. Starting to get a little bit confusing, isn't it? Yeah. But let's see what this does. Let's compile it and run it. Great, I've now got a full row. Now, I want to get a second row going. So I could simply repeat the section of code indicated by row. I could repeat that 24 times. But the problem is, you've probably guessed, it's going to begin with the black square every time, followed by the white square. And I don't want that. That would give me strips down the screen, and I'm not looking for that. I want the checkerboard effect. So what I'm simply going to do is I'm going to reproduce the code from line 4 to line 8. I'm going to double it up. And on line 9, where it says 0, I'm going to change that to 127. And on line 11, where it says 127, I'm going to change it to 0. So in other words, I'm repeating the same code, but I'm reversing the value of the colors so that I will get the opposite effect. Now, here's the thing. I've got two areas of memory, both labeled row, so I can't call them both row. So let's relabel the one in line 4 to row 1, remembering to change that also in line 8. And I'll call it row 2 in line 9 and line 13. So it's always important that these things have absolutely unique values. All right, let's compile it again. I should have 2 lines in checkerboard fashion if this works. Yeah, it kind of worked, but I've made a mistake somewhere. What have I done? Ah, of course, I forgot to reset the value of B back to 16 after I did the first one. So between lines 8 and 9, I need to insert LDB, 16 so that the loop actually works again. Okay, let's compile it again. Perfect. We've now got 2 lines in checkerboard fashion. Now we want to repeat that down the screen. We don't want to do it 24 times. It would have been 24 times if we were dealing with 1 line, but because we have 2 lines, we only want to repeat those 2 lines 12 times to fill the screen. So we need to encapsulate all of this in some other kind of loop. So because I'm already using B, I better use a different register for this loop. So way back at the beginning of the program, between lines 2 and 3, I'm going to use register A. So LDA, 12, because we want to repeat it 12 times. You notice we always do it in the fashion of a countdown rather than a count up. So there's no handy instruction like DJNZ that will automatically take 1 away from register A. So I'm going to have to do that manually myself. So above RET, I'm going to do dec A. Dec for decrement, take 1 away from A. And now we need to perform some kind of check to see whether A is 0. And the way we can do that is with a slightly different command, which is JRNZ, and again we need to put a memory location in. What that does is JRNZ checks whether the last calculation done on any register was 0. If it was 0, it ends and goes on to line 18. If it's not 0, it jumps to wherever you want to jump to. So I'm going to jump to something called loop. And that means I want to jump right back to line 3. Nope, sorry, line 4. I'm going to call line 4 loop. There we go. So let's see if this works. There we go, perfect. So there is a fairly decent first attempt at an assembly language program. It doesn't do a whole lot, but it does allow you to play with graphics and to experience the equivalent of a for next loop, and to introduce registers, how they work, how you can change the values of registers. It only gets worse from here. This is the stage where I'm at. I'm not really intending to do a lot of lessons on this, but I just wanted to provide a jumping off point for people to try and make assembly language at least a little bit intelligible because it is pretty hard to learn. Okay, folks, thanks.